Ryan, I think you're tuned to go next. Maybe you'll bust in song. Maybe you'll start telling us what are some songs from Hamilton? I can't tell you. All right, the correct answer is Ryan. Oh my God, Ryan! Maybe it is true. Maybe you are gonna bust into song. Okay. Okay. I learned a lot from this. And in particular, I learned that Ryan, are you with us?
Yeah, I'm with you.
Is it true? Or was that?
It is true. It is true. And I'm a little bit disappointed you thought that was an embarrassing fact. I'm quite proud of it. I think it's a skill. It's a skill I refined over many years.
Well done. When did you saw it in person, or you saw it how did you first watch it?
No, I didn't see it in person. No, I listened to the soundtrack first for the first couple of years, and then when they came out on Disney Plus, I watched it there, and then I finally went and saw it in person a couple of years ago.
You saw it, okay? Was it good? Just as
fantastic.
you imagined, or even
Oh, better, so much better.
Did they change the cast? I heard they changed the cast from the first set, right?
Oh yeah. It's been going on since like 2016 or something. If the same cast was doing it this whole time, oh man, I'd feel bad for them.
For people who are not well versed in it, what's the best song to look up?
Oh man.
Or one of your favorite ones?
I would go with My Shot. It's one of the opening songs, one of the first songs in the musical. It's very good.
My Shot. Okay, Ryan, this is your shot now. Do you have your screen up? You do.
I think I do, yeah.
Today we're going to talk about GPU accelerated data curation for LLMs. Take it away, Ryan.
Great. Thank you so much. I really appreciate it. So yeah, hello everyone. My name is Ryan, and I'm a deep learning algorithm engineer here at NVIDIA. And for the past year or so, my team has been working on developing tools to assist researchers in curating large data sets for training LLMs and multimodal models. And I'm coming here today to share some of the challenges that we faced and some of the lessons that we've learned when scaling our data curation efforts. In particular, I want to focus on some of the steps of our pipeline that we were able to accelerate with GPUs and share how we did it. So let me give a brief overview of what I want to cover. So first, I want to give some motivation to data curation as a whole to explain why we're doing all this in the first place. Next, I'll walk through an example pipeline of what a typical data curation pipeline looks like for LLMs and discuss where in the pipeline we start seeing bottlenecks. And then we can talk about some of the individual steps that we've looked at and GPU accelerated, starting with fuzzy deduplication, then moving on to semantic deduplication, and then ending on some classifier models. Okay, let's talk about the goal. So data curation is all in service of the model. We evaluate the effectiveness of data curation methods entirely by how much they improve the downstream accuracy of the model. As a bonus, if we can get some improved accuracy with fewer training steps, we'd like to get that too. And improving downstream accuracy through data curation typically comes from two things. The first is removing data that is actively harmful for your model to see during training. This is data that it's just better off not seeing in the first place. Second is getting the best subset of data possible for your compute budget. Often you'll have more data than you can actually train on, so it's important to train on the best data that you can with the amount that you have. So an example pipeline kind of looks like this at a high level. Let's start from the beginning at the very left. You start off with your raw data hosted on various sources. This could be like cloud storage, it could be your local workstation or your cluster. You first need to aggregate the data and then extract it into some usable form. For web data, like Common Crawl, for example, this typically involves extracting plain text from the raw HTML pages. And next, you might apply some basic cleaning and pre-processing steps. This would be something like fixing any character encoding issues that you might have in the data that are artifacts from the raw data itself or from the extraction process, or doing some simple language identification or preliminary quality filtering using some tiny n-gram models. You then might apply some kind of simple heuristics like the Gopher rules to remove documents that are too repetitive in your data set or documents that might have too much punctuation for their length or something. Very simple heuristics. Then we, in the later stages, we get into some of the beefier, more compute-heavy operations like deduplication. Typically, you want to remove duplicate records from your dataset. This is because research has shown that repeating tokens during training is usually not as beneficial as seeing new tokens. But what counts exactly as a duplicate is a little bit subjective, and there's a couple of ways we can categorize them. So exact duplicates are kind of character by character duplicates in text. And you can easily identify them by just hashing a document and hashing all your documents in the data set, and then comparing hashes to see if they're the same or not. Fuzzy deduplication is also character-based and designed for text, but instead tries to capture near duplicates as well, with documents that might only vary slightly. This could be some legal boilerplate that is common across multiple documents, but with like slight variations in the name changes, or it could be an article that heavily quotes another article in your data set. We'll discuss the exact algorithm that's kind of used for determining what exactly a duplicate is under fuzzy deduplication later. Semantic deduplication is the final deduplication method that I'll mention, that instead of looking at character level similarity of the documents, it instead tries to assess the semantic meaning of each document or image, and compare the semantic meaning via embeddings. So it'll embed each document in the dataset and then remove documents that have too similar of embeddings. Semantic deduplication is unique in the fact that it can be applied across modalities. And we'll discuss more about that later and kind of the benefits of cross-modality deduplication later. So data annotation is the last stage, where you might also want to annotate and filter data based on other signals and more complex classifiers like BERT models. And then finally, at the very end of your pipeline, you can aggregate all of your data from the original sources and from each individual curation pipeline and blend it together. And through this pipeline, you might see a pattern kind of form up. We start at the beginning doing some of the less computationally heavy stuff, some of the simple heuristics, some of the very tiny n-gram models, and then slowly build up to the deduplication and data annotation with bigger models. This is simply just because the scale of the data sets today is so large that you have to really be mindful of the data that you're processing and try and minimize the amount of data that you process with some of the more compute-heavy methods. And so speaking of scale, scale is really the primary concern with data curation right now. Llama 3.1 was trained on 15 trillion tokens, but the raw dataset size was almost certainly much larger. And several open datasets that I've listed here are based on dozens of common crawl snapshots, totaling hundreds of terabytes in raw size. And for this reason, we can't apply the heavy classifiers on all of our data. And even though BERT models are thought of as small in terms of modern LLMs, they're usually way too big to run across hundreds of terabytes of data due to the limited compute requirements that you might have. But I do want to focus in on these final two steps of the pipeline that I brought up, the deduplication and the data annotation, because that's where we saw the best ways to heavily speed up our curation. So we found that exact, fuzzy, and semantic deduplication can be accelerated with GPUs. And while BERT classifier models are typically already on the GPU, we still found other ways to optimize them for offline inference. And similarly for semantic deduplication, we've optimized the embedding creation along with the rest of the deduplication pipeline. So now let me walk you through the first step of the pipeline that I want to talk about, which is fuzzy deduplication and kind of the process that our team went through when discussing this. So we knew that fuzzy deduplication was an important part of the curation process. It allows us to identify documents that are similar on a character level, like I mentioned before. And the process for identifying fuzzy duplicates goes like this. You take your data set, which is a collection of documents, and you generate a min hash signature for every document. Min hash signatures are basically a list of hash values for a given document. And these hashes are computed in a special way, such that if two documents overlap for, say, 80% of their min hash values, the character level overlap is likely 80% as well, meaning that around 80% of the content of each document is the same between them. Now, it would be great if we could pairwise compare all of the min hash values in our data set with all the other values in the data set. But again, scale is an issue here, and that is impossible when we get to the billions of documents. So instead, we approximate the comparison by grouping the min hash signature into buckets. So remember, a signature is just a list of hash values. So grouping in this case just means segmenting the list. So if you have a signature with 200 hashes and you have 20 buckets, you'll have 10 hash values per band, or per bucket, I should say. And so then in this LSH step, we combine all of the hash values in a single band with another hash function, such that we're left with 20 hash values total. We then consider documents duplicates if any of these resulting 20 hash values are the same between two documents. We also consider like the network of duplicates here. So because a document has multiple bands in it, it will still have multiple hash values. It can collide with multiple documents at once. And so you can imagine, let's say the first and second documents in your data set share the same hash value in one band, and then the first and third share the same value in the third band. We consider all three documents to be part of one connected component of duplicates that we then try and identify and then remove their duplicates and only keep one for the training set. So our team wanted to do this at the large multi-terabyte scales, but we were running into bottlenecks on the CPU. We ran our original CPU implementation on a multi-node CPU setup, and we benchmarked it. And we had originally planned on scaling up this deduplication for orders of magnitude more data. But with our estimate, it would take weeks to deduplicate it. And our research team couldn't wait that long. And so my teammates built in a GPU accelerated version that does the entire process that I previously outlined on the GPU. We used dask-cuDF, a distributed data frame library that's also GPU accelerated, to parallelize the min-hash and LSH computations across multiple nodes. And cuGraph provided the GPU acceleration to compute the connected components at the very end of the pipeline. So the entire end-to-end pipeline now can run entirely on the GPU. And as we could see here with the numbers that I've given, we were able to drastically reduce the time that it took for the deduplication to occur. And then the figure on the right demonstrates some of the ablations that we've done with this method, and demonstrating that this deduplication provides a significant benefit to the downstream model performance compared to not deduplicating your data at all. So yeah, that's kind of the overarching view of fuzzy dedupe and one of the modules that we have accelerated with GPUs. Now I kind of want to go into a different form of deduplication, semantic deduplication, that we've it's become really popular in data curation kind of recently. And so semantic deduplication, like I mentioned at the beginning of the presentation, is very popular in multimodal models. And it works like this. You take all of your elements in your data set, whether that be text, images, or whatever modality you're working with, and you generate an embedding for each one of them. In the diagram, this generation of embeddings is just represented by populating this plot with dots. Now, we'd ideally like to compute the pairwise similarity between all of the embeddings in our data set using something like cosine similarity or L2 norm, something like that. But just as with fuzzy dedupe, the pairwise computation across an entire data set is just impossible. So as a preliminary step, we use k-means clustering to cluster the embeddings into different segments. And so here in the diagram, that's represented as assigning a different color to each of the clusters. Now we can compute the pairwise embeddings within each cluster, thereby reducing the computational complexity and actually providing a scalable solution. And we say that if two or more embeddings share or within a certain distance of each other, you can kind of tweak via a threshold, then we typically keep the one that's closest to the cluster centroid and then remove the rest. And yeah, so let's discuss kind of the importance and the impact of this method. So in the chart on the right, you can see that for image curation in particular, semantic deduplication is incredibly valuable for improving your model's downstream accuracy. In this case, it's able to match the performance of a baseline model with only half the number of training iterations. And in terms of the time spent on semantic deduplication, most of the time is spent on the embedding creation. And most folks understand that you need to run embedding creation on a GPU. But we have found some unique ways to squeeze more performance out of the embedding creation for text in particular that people might not be aware of. And so I'll discuss more on that later when I get to the classifier models. But besides that, now we also found that moving the k-means clustering step from CPU to GPU and accelerating it with cuML provides a pretty good speed up as well. The thing that we're the most proud of, though, is not really any individual speed up number, but it's kind of the scalability of this and the fact that I think we are the first open source solution that can scale to multiple nodes and multiple GPUs for semantic deduplication. And so we're currently seeing really how far we can take that in our experiments. And lastly, let's talk about the classifiers. So in particular, I want to focus on single GPU classifiers in the 100 million to 1 billion parameter range. These classifiers are typically already run on the GPU compared to smaller, like tiny n-gram models that might have only like hundreds of parameters or something. And so these classifiers are really often used at the end of the pipeline to help annotate your data set with some other quality signal. It could be a domain label. For example, if you're trying to train an LLM that's very proficient in sports, you might use a domain classifier to find all the sport data in your data sets and only fine tune or train the LLM on that. Or you can use a simple quality BERT model again to just add another layer of filtering on top of it and say, hey, I only want the highest quality documents that this more sophisticated model deems as high quality. And these classifiers, again, well, small in comparison to state-of-the-art LLMs, are still large enough that they really need to be run at the end of the pipeline and run in as little data as possible. And since these models typically already run on the GPU, you might be wondering what can be done with them at all to speed them up. And there's actually a few speedups we can get kind of for free that doesn't involve changing the underlying model at all. First, by profiling the memory usage of the model at variant sequence lengths and batch sizes, we can dynamically adjust the batch size based on the sequence lengths in the batch. This generally looks like saying, hey, if you have a bunch of small sequences, let's just increase the batch size so we utilize all the GPU memory that we have available. And for some BERT models, we can actually accelerate them with GPU tokenization. And with these methods, this is also how you can get, going back to the semantic deduplication, a speed up in the embedding creation, again, for free, without changing the model at all. Now, as you can see here, we've appellated on a quality classifier that we have that I mentioned in the previous slide and demonstrated that, hey, this is a pretty good performance boost with using the quality classifier. And again, using our techniques, we can accelerate the inference of the model by 40% without changing anything in the model. Just plain PyTorch, you can download the model and then just strap on this profiling techniques and just get a free performance boost. And so, yeah, that's pretty much it. We've learned a lot about curating data sets, and my team is really trying to share all the knowledge and the tools that we've had. I provided a link to this NeMo Curator repository. This is where all the methods and tools that I've discussed so far are being developed and have been developed and will be developed. We're adding new stuff all the time. And I've also provided a link to a documentation for NeMo Curator to help you get started. And there's also a link to the Docker container to help you can pull it down and immediately start running the code on your machine right now, right after the presentation if you want. And yeah, I'll be here for questions, obviously, at the end of this. But if you don't get your question answered or you think of something later, here's a link to my email and other ways you can contact me. So yeah, finally, credits. I want to give a huge shout out to all my teammates. My teammates deserve all the credit for everything I've mentioned here. They've been fantastic and have it's been a huge effort over the past year. And so many people have made so many great contributions to this to get this to where it is. And also thank you to the organizers for letting me come out and give a good talk on this. So yeah, I'll now take questions.
Thank you very much. This was excellent. And I was actually struggling with a very similar problem for a very long time. And this is a very tricky and pernicious problem to solve. So I want to see if other people have questions. And until they do, can you go back a few slides?
Sure.
The one with the min hash.
Sure.
And I want to know how deep I can go in terms of, okay, so.
This one?
Yeah, so let's just like break it down step by step.
Mm-hmm.
We have a bunch of documents and we suspect that there might be some duplicates there, but they're not duplicates in the typical sense, where it's not not necessarily identical documents, where you can just produce some kind of hash of the document and then compare the hashes. There's going to be something that is different here, right?
Mm-hmm. Yeah.
Okay. So, and then let's just imagine that we're dealing in just like the single like modal kind of sense. So let's say just text.
Mm-hmm.
Can you like remind us what might be one example of such a like near identical document that isn't exactly identical?
Sure, yeah. I think a good example of this would be like a legal document, for example, where you might have like a license file or something that is like very similar, has a lot of the same boilerplate across many different things, but might have different people in charge. You might say like, hey, this copyright is applied to me, Ryan, but not to you, Adam. And so it's the exact same boilerplate that comes after that, where it's like, hey, here's all the terms of service and such. But at the very beginning, you have a slight difference. And so that's one example.
And so, and even in that situation, then considering those duplicates is a function of the business requirements, right? Like the business would have to tell you kind of like for what purposes, because I can imagine situations where you wouldn't want to deduplicate. Both of those might sound totally different, right? But if, for example, all you're doing is looking for templates of documents, well, then yes, in that case, they're like virtually the same. So is that that's one way for us to think about it, right? Like there isn't just like a one right answer here. There's like a business dependence.
Sure, yeah, sure. This is a very business dependent. What I'm talking about in this presentation and what I focused on was more for the foundation model pre-training kind of side of things, where it's like, okay, when you're feeding like trillions of tokens to an LLM, you don't really want to see repeated tokens more than like 4 times, because then you're just kind of wasting compute when you could be seeing fresher tokens and get better performance out of your model. Yeah.
Great. So it's almost like just increasing diversity.
Yes, exactly.
And then like minimizing cost of just, you don't want to just train on the same thing over and over again.
Exactly.
Okay, great. So now we took those documents and we computed min hash for them. Do you know how that's done?
Yeah.
Tell us a little bit about that.
Yeah. So the min hash, it's a very interesting idea. So essentially what you end up doing is the min hash is kind of an approximation of this Jacquard similarity. This is what it's called. And so what Jacquard similarity does is it basically takes a sliding window over your text, let's say of like 20 characters or something. And so what you might have is you might have like a sliding window over your text that's 20 characters long. And so you start with the first slide, you start with the first window, you slide it over 1 character, then you have a new window. In a perfect world, you would save all of these windows. And so you'd end up with like a giant list of windows of characters. And you'd do this for every document in your data set. And then what you would do is you would compare each list between the 2 documents. And so you'd say, hey, I have this 20 character element in this list. Is it in this other document as well? And you would do this for each document in the set, or pardon me, each window in the set for a given document. And then the amount of windows that are the same or common between them is kind of the amount of overlap that you have between your documents. And so what min hashing does, it says, okay, I can't do that because that's a really expensive operation if your documents are big. And so what I'm going to do instead is take a hash value of each window. In particular, I'm actually going to take several hash values. I said 200 in my example. And so I'm going to hash each window 200 different times. And then cumulatively, every time I do that for each window, I'm just only going to retain the minimum value of each hash across each window. Okay, so that looks like saying,
so you took each window. For each window, you came up with like multiple hashes?
Yes, you hash it using 200 different functions.
Oh, different functions. And they, how do they, okay, so you just run like different hashing functions?
Yes.
Totally different, okay. And then, okay, so now you have, let's say like 200, let's say you have 200 different hashing functions per window. So now you, okay, so now you have 200 values per window, and then you have 200 values per other window.
Yep.
And then so, you try to find that, yeah, go ahead.
And then so for each one of these hashes that you've generated, each one of these 200 across all of your windows, you just take the minimum one of each hash. So each hash is just an integer, and so you just take the minimum one of each one. And this apparently is mathematically proven that this is a good approximation for the Jacquard similarity, because then you can do a set comparison between, instead of all the windows, just of the min hashes of each set, and say, hey, how much overlap is there between the min hashes of one document versus another document?
Okay, so the min hash might turn out, let's say for my first 20 characters, might come out to be 5.
Yeah.
Right. And then we go to another document, and you look at any one of those windows, and it comes out to be 8.
Yep.
Right. This is the min hash for each one of those.
It's one of the min hashes, yes.
So for wait, it's the min hash for each window. It's the minimum. It's the lowest number for each of those windows.
Yeah. So the important thing to remember here is that at the end of the day, what we're getting is a list of hash values. So each document is going to go to a list of hash values.
Right.
And so, yeah, so for a given document, you might have one of the hash values is 5. And for the other one, it might have one of the hash values is 8. Yeah. And so in that case, you'd say, okay, that's not uncommon. That part of the document, or I say part of the document in a very abstract sense, but that part of the document is not the same. But you might have another hash value that says, oh, this is 10 and this is 10. And so in that case, okay, these are the same. And so you have some similarity between the documents here.
Got it.
Because you know that for some window of text, they share the same value.
Right. Okay. So it's identical. We're looking for almost like identical. They're unlikely to be the same if they're different. If any one of the windows is, if all the windows from one document are totally different from windows in another document, then we're saying they're just like maximally unsimilar.
Yep.
Okay, that's right. So it's because there are other algorithms that might play a similar game, but with like string edit distance. That's not what this is.
No, not string edit distance at all. Nope.
Great. Okay, this is just straight up overlap.
Yep.
That we're comparing. Great. Now you took this and then you put it into these buckets.
Mm-hmm. Yep. So the idea here is that, okay, we would ideally like to say, hey, you've got 200 values for each document or data set. Let's compare all of them with each other and compare the overlap. So you have document A and B. We know that, okay, 50% of the hash values are the same between the two of them. And so we're going to say that they're 50% equal. We'd love to do this, but we can't because it's too big. The data set's too big. So what we do is we do an approximation where we try and figure out, okay, we do an approximation where we split up the min hash signatures into individual components. So this would be like, we group it basically. So let's just imagine taking one group of this. So we have 200 signatures to begin with. Now let's just take the first 10 and let's hash them again. Let's combine them together and hash them again. And then we do this for the other document. We combine them together and hash them again. Now, we're only going to get a collision if they're all the same, right? But we do this like 10 unique times. And so at this point, we use this approximation to say, okay, if any one of these 10 collisions occurs, then we consider it a duplicate.
Got it.
And that the intuition behind that is that we're kind of saying like, okay, if at least like a good chunk of the first part or of some part of the document overall is the exact same as a good chunk of another part of the document overall, we can say that, okay, they're probably overall duplicates.
LSH, by the way, there's the local sensitivity hashing?
Yeah, locality sensitivity hashing.
Okay. Nice. Okay. And then you put that as you're looking for connected components, and then you keep the one that is closest to like the centroid, and based on some kind of radius. Yeah, go ahead.
Yeah, there's no centroid here, sorry. So we get the connected components where we say, hey, we've got, we know that these two documents overlap in one band. They have the exact same value in this one band. But there's multiple bands in each document. And so you may have document A that has the same band as document B in the first spot, but then like the 7th spot or whatever, it shares the same band value as document C. In this case, it's like D0 shares the same band, first band with D4.
Yep.
And D0 also shares the same band, the first band with Dn-1.
Right.
But here you can see Dn-1 shares like the last band with D5.
Yeah.
And so theoretically, you actually could connect these, or you probably should connect these in the diagram to be here and here, have this connection right here, where you're saying, okay, within each bucket, sure, you have a connection, but across buckets too, you now have a connection because you know that one document was the same as this document, and this document is the same as this document. So by transitivity, they should all be roughly the same.
Do you ever have a situation where you have to tweak maybe even like the number of buckets, because otherwise you're just going to get like massive connected components where all of them basically share enough in common with another one, and so all of them end up gluing in?
Yeah, that is definitely a parameter you need to tweak and be aware of. I think we've typically found that I think it's like 20 buckets is what we use, or 20 bands roughly is what we use, and that's good enough because each band, to be clear, is like a 32-bit integer or something, and so you need an exact collision in that 32-bit integer in order for it to register as like a duplicate. And so when you have 20 bands with 32-bit integers in each one, usually that's good enough for like the multi-terabyte scale we found.
Makes sense. This is fascinating, by the way. I mentioned I had worked with a similar problem, and I was trying to use this like a similar kind of solution, and I couldn't quite get that to work because I think for me, like the use case that I had, I simply couldn't tolerate any inaccuracies. Yeah, and so I really needed to fully explain every one of the steps, and it was a smaller data problem, but I bumped up against the combinatorial challenge of having to make these comparisons. So I was dealing with like 100 million records, and having to make comparisons between all of them. It was for like an entity resolution kind of deduplication situation. The moment you try to make comparisons across, everyone, now it's just like it's an n-squared problem, and it blew up. So I needed to find different ways to, I think they called it like blocking, like coming up with these blocks. Where you can then make comparisons. And I think it's similar to your buckets a little bit.
Yeah, it's very similar to the buckets. All these have it's similar to the buckets and probably very similar to the clustering step.
That's right.
And the semantic duplication. Yeah.
Very cool. Ryan, thank you very much for sharing this with us. This is fascinating.
Sure. Yeah. Thank you so much for having me. I appreciate it.
Yeah, thanks.